After discussing the features of the DCM model, so in this section, we are going to introduce how can we establish the model for DCM operation. So we are going to use the average switch model we have learned in the last lecture. So first, let's have a review of the DCM operation. So we are going to use the buck boost topology as an example. First, let me plot the schematic of a typical buck boost converter. So here is the input source as VG. And here we have a power MOSFET, Q. And here we have an inductor, L. And here is the diode, D. Filtering capacitor, C. And the load resistor, R. We marked the output voltage as positive on the upper side. So we can denote several parameters in the schematic. First one is the inductor voltage as VL. And now second one is the inductor current, IL. Based on the DCM, discontinuous conduction mode operation for this circuit, we can first establish the DC large signal modeling for this converter. So we can plot the time domain waveforms for those quantities, inductor voltage and inductor current. They are the key threads for us to solve the circuit operation. So time domain. So top one is the inductor current. Bottom one is the inductor voltage. So for DCM operation, there are 3 segments in one switching cycle. Suppose here is 0. So here is the mode 1, D1 TS. And here is the mode 2, D2 plus D1 TS. Here is TS. So the inductor current will be rising linearly in operation mode 1, starting from 0, because this is DCM. And the slope of the straight line here is equal to the voltage divided by inductance. For mode 1, it's VG over L. And Q is on in mode 1, right? So the inductor voltage will be equal to the input voltage. So the level here will be equal to input voltage, VG. In mode 2, Q is off. Diode conduct to continue the inductor current so that the inductor current will be dropping linearly. And the voltage across it will be equal to the output voltage, right? D is on, so the voltage equals to output voltage. So value here is V. V is indeed a negative number. This is because buck boost is a inverting DC to DC converter. The polarity of output and input voltage are inverted, so that the inductor current will be dropping linearly. The slope equals to the voltage divided by inductance. And the duration for mode 2 is D2 TS. Here is D1, right? So after the inductor current hits 0, the circuit enters into the discontinuous mode. So the inductor current will remain equals to 0. Both switches are off. So since inductor current is 0, so the voltage across it is also 0. So that's the complete waveform. Based on this profile of the inductor current, we can derive the height of the inductor current, which we denote as I peak. So I peak can be easily solved, right? So basically, I peak will be equals to the duration times the slope, so which is Vg over L times D1 Ts. And next, we can apply volt second balance to the inductor voltage. So the average inductor voltage should be equal to 0 over one switching period at steady state. So based on the profile, we can easily derive it, right? So it's D1 times the level here plus D2 times the level here. D1 average input voltage plus D2 average output voltage plus here is 0. So the volt second balance tells us the average inductor voltage equals to 0. And based on this volt second balance principle, we can find out the relationship between D1 and D2. So basically, we will see that D2 can be represented by D1 as minus D1 times average V input voltage average over output voltage average. Okay. So the average input voltage divided by the average output voltage. And next, think about the average switch model we have previously studied. So based on the schematic, we can extract a two-port network which circle the switches. Here it is, switch network. And we define the input port and output port. Right? Port 1 is the input port. So here is the input port voltage we denote as V1. And this is input port current we denote as I1. Secondly is the output port. So it's here, plus minus V2. And this current is I2. So based on the circled switch network, we can analyze the averaged switch model. By plotting those four quantities, V1, I1, I2, and V2. So first, let's plot their waveforms based on the DC operation we listed here. So four waveforms. in time domain, which includes the port 1 current I1, port 1 voltage V1, port 2 current I2, port 2 voltage as V2. We denote the 3 segments in one switching cycle, respectively. So here is the D1 TS. Here is D1 plus D2 TS. Here is TS. So first, look at the I1, the input current for port 1. So when the Q is on in mode 1, diode is off, so I1 equals to IL. And the voltage V1 equals to 0. Right? Q is on, so we consider it's ideal switch, so the voltage drop is 0. I2 will be equal to 0 because diode is off. V2 will be equal to the difference between the input voltage and the output voltage. So next, let's look at the mode 2, right? Mode 2, the Q is off, D is on, so the current of I1 equals to 0. And the voltage V1 will be equals to Vg minus V. Right? Q is off, diode is on. So the KVL tells us that this voltage equals to input voltage minus output voltage. And I2 will be equal to the inductor current. And V2, right? V2, because diode is on, so if a diode is ideal, the voltage drop will be equal to 0. And thirdly, we look at the mode 3, right? Mode 3. So the both Q and D are off, and the diode inductor current remains 0. So this current will be remaining 0, and this current will also remain 0. So the V1, right? Because the Vg is here, the inductor voltage is 0. So based on KVL principle, we can solve the V1 in mode 3. It will be equal to the input voltage Vg. And V2 is here, right? Since the inductor voltage is 0, so the V2 will be equal to the minus output voltage based on KVL principle. Then it repeats, right, after one cycle, repeats. So that's the full profile for those two-port network. And based on this profile, we can analyze the 2 parameters, right? First one is V1. So based on KVL, we can list the formula for V1 from KVL. V1 will equals to the input source voltage minus inductor voltage. So based on this KVL principle, we can also apply this relationship in the average expression. So V1 average equals to input average minus inductor voltage average. So in steady state, we have the volt-second balance, meaning that the average voltage of inductor equals to 0, right? So this part is eliminated. Therefore, the right-hand side can be equal to the average input voltage. And next, let's look at the output port voltage, V2. So V2 can also be expressed based on the KVL. V2 equals to the inductor voltage minus output voltage. Similarly, we also do the average on both sides at steady state. So volt-second balance tells us that this one is 0. So the right-hand side is simplified as minus output voltage average. So next, we can look at the peak current expression. So peak current expression can be simplified accordingly. So I peak will be equal to the average input voltage over inductance D1 TS. So see here, the input voltage average equals to V1 average. So we replace VG by V1. And we are going to keep it here for future usage. And secondly, we look at this formula, right? We also can replace the VG and the V by V1 and the V2 accordingly. So like we can derive that D2 over D1 equals to minus VG over V equals to average V1 minus average V1 divided by average V2. So because here is another minus, right? So the two minus are canceled. So we replace this by positive. Okay, we have erased the left-hand side of the blackboard. Now let's continue analyze this switch model. So we have plotted their waveforms of I1, V1, I2, and V2. Now let's analyze their average values, expressions one by one. So first, let's look at the average of I1 over one switching period. So I1 will be the average over TS. So based on the profile, we can see that it should be equals to the area, right? Of this triangle, which we mark as Q1, divided by the entire period. And this Q1 can be easily solved by the area formula for the right angle triangle, right? So basically, it's like 1 over 2 base times the height. 1 over 2. The base is the D1 TS. Height is the peak current, right? I peak. divided by TS. So we will see that the two TS in the numerator and denominator, they can be cancelled. And we insert the expression for I peak into here. The I peak is here, right? We insert I peak to here. So we can simplify the expression. This will be 1 over 2 d1 square TS times V1 average over L. Therefore, we can simplify the right-hand side, right, by combining the coefficients together. So we will see that the conclusion is that I1 average equals to d1 square TS over 2L times V1 average. And secondly, let's look at the average I2 for the output port in this extracted switch network. So similarly, we look at the profile of I2. The integral is the area of the right-angled triangle. So let's mark this area as Q2. Q2 is the this triangle's area, which is the 1 over 2 base times height. Q2 over TS. 1 over 2 base is D2 TS. Height is still I peak. Again, the TS are cancelled. And we insert I peak expression back to here. So this is 1 over 2 V1 average over L D1 D2 TS. So D1 is the actively controlled parameter. Well, D2 is depending on D1, so we wish that we can eliminate D1. Yeah, this formula gives us the relationship between the D2 and the D1. So D2 will be equals to D1 times V1 over V2 average. So we can eliminate D2 by inserting this formula to the right-hand side. So the result will be I2 average equals to D1 square TS 2L times V1 square divided by V2 average. So those two formulas are the conclusions we made. So in this section, we utilize the buck boost topology as the example, and we utilize the average switch modeling method to analyze the discontinuous conduction mode. Next, we are going to plot its equivalent circuit model of the DCM buck boost topology.